So we're going to continue looking at proving an identities. So we want to show algebraically that the left side of a statement is equal to the right side. So we're trying to show that they're equal. We can't assume that they're equal, even though if you're asked to prove an identity, it can be done. But you cannot assume that they are equal until you show it. So again, because of that, you cannot move things from one side to the other. You can only do that if you have an equation where you know two things are equal to each other. And that's the point. They're trying to show that they are equal. So you cannot move things from one side to the other. You cannot square both sides, square root both sides. You can't do any of that. You have to work down either one side or the other or both sides to show that you get the same expression on both sides. So this first example says to verify that that statement is correct for some values of x. We'll determine the non-permissive values in degrees, and then we'll show that it is true for all permissible values of x. So when it says verify that it is true for some value of x, we just choose a random angle. And it makes sense to choose an angle that's on the formula sheet. It also makes sense to not use one of the points, not on the formula sheet, on the unit circle. It also makes sense not to use points on the axes because on some of those points on the axes, the cosine is 0 and some of them the sine is 0. So for example, on the right side, if you chose a point on either the x or y axes, the right side would equal 0 because both sine and cos are one of the factors there. And no matter where you are on the x or y axes, either sine or cos is 0. Also, on some places on the x and y axes, the tan or cotan doesn't exist. So we want to use one of those other three stops in the first quadrant of the unit circle. Pi on 6, pi on 4, or pi on 3. It doesn't matter which one. So let's just randomly choose pi on 6. So for part A, we want to show that 1 minus the sine of pi on 6 all squared is equal to the sine of pi on 6 times the cosine of pi on 6 times the cotan of pi on 6. At pi on 6, the coordinates there are root 3 over 2, comma, a half, and the tangent was 1 over root 3, which we rationalized to root 3 over 3, but the reason I'm leaving it as 1 over root 3 is because on the right side we are asked for the cotan of pi on 6, which is the reciprocal of the tangent. So it's much easier to take the reciprocal of 1 over root 3 than it would be of root 3 over 3. So we're going to show that we get the same expression on both sides. The sine of pi on 6, remember sine is the y value, that would be 1/2. So it would be 1 minus 1/2 all squared. When you square half, you're going to get a quarter. And 1 take away 1/4 would be 3/4. That's what we get on the left. We need to get the same thing on the right side. Again, the sine of pi on 6 is a half. That's multiplied by the cosine of pi on 6, which is root 3 over 2, times the cotan, which is root 3 or root 3 over 1. So when you multiply top times top times top, 1 times root 3 would be 3 over 2 times 2 times 1. You get the same value on both sides. So we've shown that it is true for a specific angle, pi on 6. Non-permissive values. So they come from wherever you have denominator. And on the right side, you'll have cotan, which is cos over sine. So that's the only place where we'll have a denominator. It comes from the factor cotan x, which is cos over sine. So we would say in this case that sine x cannot equal 0. And the sine of x equals 0 at 0 degrees and at 180 degrees. and every multiple of 180 degrees after that. So x cannot equal 180 n degrees, where n is an element of integers. And we saw yesterday that you could use your graphing calculator to check that. Right? If you put first the left side of the equation into y1, 1 minus the sine of x all squared. So again, you'll have to put the sine of x in brackets so you can square it. And the right side, sine x times cos x times cotan x, which we have a couple options there. We can go 1 divided by tan of x. And actually that, when I say it like that, that tells me that I've missed some of my restrictions. Because when you write cotan as 1 over tan instead of cos over sine, but if you write it as 1 over tan, then that makes both sine and cos restrictions. If you write cotan as 1 divided by tan, now you have a denominator of tan, which means that neither sine nor cos can equal 0. So when I write it or think of it in that way, that tells me that I've missed some of the restrictions. The restrictions are actually every multiple of 90 degrees. So we'll fix that here in a second. 1 divided by, in brackets, the tan of x. So if I'm working in degrees, I need to go from negative 360 to positive 360 and a scale of 90. For y, I'll go from negative 10 to positive 10 and a scale of 2. So now when we hit graph, the two graphs are the same, but when we go into our trace mode and I want to be on equation 2, this shows me that 0 is a non-permissive value. When I go to 90 degrees, it's also a non-permissive value. When I go to 180 degrees, it's also non-permissive. Negative 90 is non-permissive because we don't get any y value returned there. So again, I need to fix this. Neither sine nor cosine can equal 0. So my restrictions are actually every 90 degrees. So once again, saying that cotan equals cos over sine, although it's correct, it doesn't give you all the restrictions. You have to think of cotan as being 1 over tan to get all the restrictions. But again, it's not enough to show that it's true for a specific angle like we started by doing. It's not enough to show that the two graphs are the same because they're only the same between whatever domain you've chosen. It's possible that there's a spot somewhere outside that domain where the two graphs are not the same, which is why we have to do it algebraically. We start with the original statement, and we use those hints that we talked about yesterday to get the same expression on both sides. So 1 minus sine squared x. From the Pythagorean identity, remember that equals cos squared x. From that Pythagorean identity. I said this is the one that you're going to use most often. Sine squared theta plus cos squared theta equals 1 or one of the variations of that. On the right side, there's no powers. So our hint when that happens is to put everything in terms of sine and cos. Cotan again is cos over sine. So what happens here is that the sine x's cancel. Right, those three factors are multiplied together. You've got a factor of sine x on the top and the bottom. They will cancel. And you're left with cos x times cos x, which is cos squared x. So we've shown that the two sides are equal. We've proven the identity. So that one is done. All right. So the next one, determine the non-permissive values for that equation. Verify it either graphically or by choosing one value for x and then prove it algebraically. So we'll start with the non-permissive values, wherever we have a denominator. So the fact that tan x is in the numerator means that only when you take tangent as sine over cos are you going to get a non-permissive value. So because tan x is a factor of the top on the left side and tan is sine over cos, we would first say that cos x can't equal 0. But also you've got a denominator of cosecant, which is 1 over sine, so sine x can't equal 0 either. And so again, our restrictions on x are that they cannot equal every multiple of 90 degrees, which we will confirm using our graphing calculator, because part B says we can show graphically that the statement is probably an identity. So in y1, again, we'll put the left side of the statement in brackets. I'll go tan of x times cosine of x. I put it in brackets because it's all divided by cosecant, which is 1 over sine x, so I need to put that in brackets as well. And I had one too many brackets there. And that should equal the right side, which is 1 minus cos squared x. So 1 minus, in brackets, the cosine of x all squared. So I'll leave my windows the way they are. Looks very similar to the same graph that we just saw in the last one. And again, the two graphs are the same, so that means it's probably an identity, but there could be a spot somewhere outside there where they're not. Yes? Yeah, no, it doesn't matter. In the last one, it said degrees. My windows were already in degrees in my calculator, so that's why I'm doing it in terms of degrees. But no, unless you're specifically told otherwise, you can use whichever one you want. I just kept it in degrees because my windows are in degrees in the calculator. So again, to check the non-permissive values, we want to be in that first equation for sure, because that involves the tan and the cosecant. That's where we got our non-permissive values from. Notice when you hit trace, the calculator normally defaults to the y-intercept where x is 0, and there is no y value returned. So that confirms 0 is non-permissive. Go to 90, no y value, confirms that's non-permissive. Same thing with 180, same thing with negative 90. So we're just confirming every multiple of 90 degrees is non-permissive. And then part C, we want to show algebraically that they are the same. So start with the original expression, always. And on the right side, again, by that Pythagorean identity, 1 minus cos squared x is equal to sine squared x. On the left side, we've got no power, so we'll go back to that hint where we're going to put everything in terms of sine and cos. Tangent is sine over cos, and that's multiplied by cosine of x over 1, which is then divided by cosecant, which is 1 over sine of x. So a couple things we can do here. We can cancel the cosine x's on top and bottom, which leaves us with sine x over 1 times the reciprocal of 1 over sine x, which is also sine x over 1. Sine x times sine x is sine squared x. So now we've shown that the statement is an identity. We've proven the identity. Okay, so don't forget, if you're asked for your non-permissive values, they come from the denominators. You can always check them on your calculator to make sure that you haven't missed any, that you have the right ones. Okay? So this next example, we're just asked to prove the identity. We're not asked to find any non-permissive values. We're just asked to prove the identity. And this one involves some double angle identities. The left side, though, is just simply the tan of x, which you could write as sine x over cos x if you wanted to. But on the right side, we need to use the double angle identities. And remember, for cos 2x, there are 3 different double angle identities. Cos 2x, we saw, equals cos squared x minus sine squared x, or 2 cos squared x minus 1, or 1 minus 2 sine squared x. They all 3 will work. One will probably be easier than the others. One will be harder than the others. Just when I say harder, it's just going to take more steps. But they will all work, and they're all on your 4-minute sheet, so you don't have to memorize them. So looking at what I have, it's 1 minus the cos of 2x. Probably the easiest way to do this would be to use 1 minus 2 sine squared x. And I put it in brackets because it's all being subtracted from the 1. And the reason this is probably going to be the easiest is because the 1's are going to cancel. When you remove the brackets, all the signs inside change. And you'll get 1 minus 1. They will cancel. The denominator is sine 2x. There's only one option for that. 2 sine x cos x. Again, it's on the formula sheet. So as I said, when you remove the brackets, the signs all change. The 1's cancel, and on the right you'll have 2 sine squared x over 2 sine x cos x. You could not have canceled the 2's prior to this because, remember, you can't cancel part of a expression. You have to be able to divide all terms by the same value. But now, because we have a single factor on the top and a single factor on the bottom, now you can divide top and bottom by 2. You can also divide top and bottom by 1 factor of sine x, and you're left with sine x over cos x, which is what the left side is. So it's done. We've proven the identity. So again, most of these can be done in 2 or 3 fairly simple steps. You try something. If it doesn't work, you try something else. Remember those list of hints that you were given yesterday. If there are no powers, put everything in terms of sine and cos. If there are powers and they're power 2, look to those Pythagorean identities. If there's powers higher than 2, see if you can factor. Sometimes you're going to have terms that are going to be added together. Get a common denominator to combine them. Okay? And then the last hint was sometimes you need to multiply by conjugates, and we'll see examples of that today, where conjugates will be used. All right, so this next one, very similar, because you've got tan x by itself on one side. The difference is that the numerator and denominator have been switched around. Here we have the sine 2x on top instead of the bottom. And also the cos 2x is a little bit different because the previous one, it was 1 minus cos 2x that was on the top. This one is cos 2x plus 1 on the bottom. But it doesn't change the way it's done. You're going to use the identities that we already know to do this. So the right side is tan 2x, which is sine x over cos x. And on the left for sine 2x, there's only one option, 2 sine x cos x. On the bottom, though, we have those 3 options, and it doesn't matter which one we use. They will all work. So for no reason, I'm going to use cos squared x minus sine squared x. It's probably not the easiest way to do it, because probably the easiest one would be to use 2 cos squared x minus 1, because then the minus 1 plus 1 would cancel. Okay? But they will all work. It doesn't matter. And so the reason this one works, on the bottom, I'm just going to rearrange those last two terms. So I've got positive cos squared x, and then I'm going to put the plus 1 and then the minus sine squared x last. Because what does 1 minus sine squared x equal? What does 1 minus sine squared x equal? Cos squared x, from that Pythagorean identity. So I have 2 sine x cos x over the first cos squared x plus, once again, 1 minus sine squared x is also cos squared x. And so now you can add those cos squared x together on the bottom. So you have 2 sine x cos x all over 2 cos squared x's. And now we can start to cancel. We can divide because we have single factors on the top and on the bottom, or single terms, I should say. On top, we've got 3 factors. On the bottom, we have 2. Actually, 3, because cos squared x is cos x times cos x. But we can divide top and bottom by 2. We can divide top and bottom by 1 factor of cosine x, and we're left with sine x over cos x, which is what we had on the right from the tangent. So that one is done. Right? We've shown that we had the same expression on both sides. We've proven the identity, which means that it's true for all values of x except where we have non-permissive. So this next one is one that we will use conjugates for. And so we're going to work down just one side, right? Everything's already in terms of sine and cos. There are no powers, so we can't do any factoring or use any Pythagorean identities. But in this case, I'm going to use conjugates. And you can work down either the left or the right side. I'm just going to choose to work down the left side, which is 1 minus cos x over sine x. And I say we're going to use conjugates. What we're going to do is we're going to multiply top and bottom by the conjugate of 1 minus cos x. So the conjugate, remember, is what you get when you factor difference of squares. Same two terms, but with the opposite sign in between. The conjugate of 1 minus cos x is 1 plus cos x. And whatever you do to the top, you have to do the same thing to the bottom. We're not breaking any rules here. Remember, we said you can't move things from one side to the other. You can't square root both sides or square both sides. That's not what we're doing here. We're multiplying top and bottom of a rational expression by the same thing, so we haven't changed value. It's no different than taking a fraction like saying 5 over 3 and multiplying top and bottom by 2. You'll get 10 over 6, but it's equivalent to what you started with. So when you multiply out the top, front terms 1 times 1 is 1. The outer products will be positive cos x. The inner products will be minus cos x. And the last, a negative times a positive is a negative. Cos x times cos x is cos squared x. Now, if you look at what the right side is, it's sine x over 1 plus cos x. So because of that, I'm actually not going to multiply out the denominator, because the denominator has a factor of 1 plus cos x, which is what we need on the right side. So that is the reason that I'm actually not going to physically multiply out the bottom. But I can simplify here because the cos x minus cos x's cancel on top. That always happens when you multiply by conjugates. So I'm left with 1 minus cos squared x over sine x bracket 1 plus cos x. So on top we have 1 minus cos squared x, which equals sine squared x. Again, from that Pythagorean identity. 1 minus cos squared x is equal to sine squared x. And now we have a single term on top. We have two factors on the bottom. We can divide top and bottom by a factor of sine x. And you're left with sine x on top, 1 plus cos x on the bottom, which is what the right side was. Sine x on top, 1 plus cos x on the bottom. You could have done the same thing just working down the right side and multiply by 1 minus cos x. That's the conjugate of the denominator. Multiply bottom and top by 1 minus cos x and just work down the right side. You would have got the left side. So either way works. So a few more steps than what we have been seeing, but there's nothing really difficult about what we did. It's just one extra strategy that sometimes needs to be used. And then some algebra and some substitutions. Okay. So again, this next one's going to take a bit more work, a few more steps, but it's not going to be anything all that hard as far as the processes that we're going to use. Remember, we said to always work down the more complicated side first, which in this case looks like it's the right side, so that's what I'm going to do. I'm going to work down the right side. And again, it might take a few more steps than some of them, but that's fine. So we said we're going to work down the right side. There are no powers there, so we can't use the Pythagorean identities or factoring. So when that happens, we put everything in terms of sine and cos. So secant is 1 over cosine of x minus sine x, which is sine x over 1. That's multiplied by secant x again, which would be 1 over cos x as well. And that is being divided by cosine x, or cosine of x over 1. So when I multiply these two together inside the square brackets, I'm going to get 1 minus cosine of x minus sine x over cos x. And instead of dividing by cos x over 1, I'll multiply by the reciprocal, which is 1 over cosine x. And just so happens that inside the square brackets, I have a common denominator already. So it's going to be 1 minus sine x all over cosine of x times 1 over cos x, which I can multiply top times top, bottom times bottom. And I'm going to get cos squared x on the bottom. Cos x times cos x is cosine of x all squared, which is cos squared x. So I'm not done yet, obviously. I need to get 1 over 1 plus sine x. That's what's on the right. So next what I'll do is I'll take the cos squared x and I'll replace it with 1 minus sine squared x. And that comes from that Pythagorean identity. Normally we're going to make things simpler, but in this case we're actually going to expand it a little bit. And you'll see why I chose to do that in a second. We cannot cancel the ones right now because you're canceling parts of binomials. Can't do that. And for the same reason, you cannot divide top and bottom by a factor of sine x right now because you're canceling parts of binomials. Can't do that. However, the bottom is a difference of squares, so we can factor it as a difference of squares. The factors would be, well, the square root of 1 is 1. The square root of sine squared x is sine x. One's a plus, one's a minus. That's how you factor difference of squares. And now we can cancel. There is a factor of 1 minus sine x on both the top and the bottom. Those will cancel, and you're left with 1 over 1 plus sine x, which is what the left side is. So we're done. A few more steps there, but again, nothing that we haven't seen before. Now you could have started the right side by taking out a common factor of secant x first. So what would that have looked like? So I'll just show you that. We would have taken this and taken out a common factor of secant x first. You would get 1 minus sine x all over cos x. And because secant is 1 over cos x, you'd have 1 and 1 minus sine x on top. On the bottom, you'd have a cos x that came from the secant, which is 1 over cosine, times another cosine on the bottom. That would have given us 1 minus sine x over cos squared x, which is exactly what we got right here. Same thing. So we would have worked through just like we did to finish it off. So this just shows you, and I mentioned this yesterday, often there's more than one way to do it, to get started. So originally I did it by putting everything in terms of sine and cos and then simplifying from there. Now we see we could have taken another common factor of secant x, which may have saved us a couple steps maybe. But in the end you get the same thing. Okay? So we said sometimes you're going to need to factor, and you always work down the more complicated side first, which in this case would be the right side. We may have to do some work on the left side, but we won't know until we finish as much as we can do on that right side. So that's where we will start. So remember, for cos 2x, we have 3 different options. In this case, it will matter which option we choose. Because on top, you have a term that's just cosine x, because of that, I'm going to choose the option for cos 2x that only contains cosine, which is that cos 2x is 2 cos squared x minus 1. And then you've got your minus cosine x, which was there already. On the bottom, we only have one option for sine 2x, and that is 2 sine x cos x. And then you have that plus sine x that was there at the start. So we're going to factor both the top and the bottom on that right side. But before I do that, I should rearrange the terms. On top. And now we'll factor. The top is a trinomial. There's no common factor there, so the factors will be binomial factors. The front terms multiply to get 2 cos squared x, so it'll have to be 2 cos x and cos x. The last terms multiply to get -1, and when I FOIL it out, I have to get a -1 cos x in the middle, which means that the -1 has to be with the cosine x, +1 would have to be with the 2 cosine x. When you multiply those out, the outer products will be -2 cosine x, the inner products +1 cos x. They become -1 cos x. And on the bottom, there is a common factor of sine x. And if you take it out, you'll get 2 cos x plus 1. Common factor of sine x on the bottom. And now we have a factor of 2 cos x plus 1 on both the top and bottom. They will cancel, and we are left with cos x minus 1 all over sine x. Which is not what we have on the left side, so we need to do some work on the left side to get the same expression we have on the right side. And that's one option. But the other option is continue to work down the right side. If you have a binomial divided by a monomial, you can say, well, that's the same thing as both terms on top divided by what's on the bottom. And cos x over sine x is cotan x, minus 1 over sine x is cosecant x. Now we have what's on the left. Now we have what's on the left. Or we could have stopped right here and worked on the left side, and we would have got that same expression. It doesn't matter. As long as you get the same thing on both sides, you've proven the identity. Okay. So for this one, we're going to have to work down both sides. Sometimes the pieces that look like they're going to be quite complicated turn out to be not that bad, because factoring can really simplify an expression quickly. So I said, in this case, we're going to have to work down both sides. So let's work down the left side first. For sine 2x, you have only one option. That's 2 sine x cos x. And for the denominator, that's a difference of squares. Binomial, both terms are perfect squares, minus sign in between. When you factor difference of squares, remember you get conjugates. The square root of 4 sine squared x is 2 sine x, I should say. The square root of 1 is 1. 1's a plus, 1's a minus. On top, there is a common factor of cosine x that we can take out, which will leave us with 2 sine x minus 1. And so the 2 sine x minus 1s will cancel. And we are left with cos x on top over 2 sine x plus 1 on the bottom, which we will leave there and then move to the right side. So on that right side, as soon as you see that cos cubed x, that should be a hint to you that you're going to have to factor. None of our identities involve cosine cubed or anything cubed. But there is a common factor of cosine x on top that if we take out, you're going to be left with sine squared x plus cos squared x. And our denominator is 2 sine x plus 1, which is what the denominator is on the left side. So that's good. What now, Adil? To what? That's right. From the Pythagorean identity, sine squared x plus cos squared x equals 1. So it's going to be cos x times 1, which is just cos x on top, over 2 sine x plus 1 on the bottom. Now what, Sathuni? Pardon me? That's right, we're done. So now what? We celebrate. Yay! Did it ask us to do that? No, it said to prove it for all permissible values. Okay, this is me never minding. Okay? So yeah, I mean, you looked at that right side and you might have thought, oh, Jesus, this is going to take a lot of work. But by factoring, quite simple, actually. Okay? So again, you've got that list of hints. Use them. Try something. If it doesn't work, you try something else. Most of them can be done in 2 or 3 fairly straightforward, simple steps. We saw some today that took a few more than 2 or 3, but it was nothing all that complicated. Just a little bit of algebra in most cases, which you have been doing for quite some time in high school mathematics. All right. So there's a worksheet there. It's got 2 sides. You're going to hand this one in for marks. Okay? So Monday and Tuesday, we're going to do some work with using these trig identities to solve equations. So we'll spend a couple days on that. And then you'll have your quiz on Tuesday. And then your exam on Thursday. So Wednesday, we'll be going through, I guess it looks like the chapter 5 and 6 quizzes, because I still have one person left to write the chapter 5 quiz. So I'd like to have that done before we go through it. And then you'll also have some time to work on the review assignment, which you guys got yesterday, right? So if you didn't get that, then you need to ask me for a copy of that. And I would recommend that you start working on that over the weekend. If you can do everything on that review assignment, you'll be fine or prepared for that test on Thursday. So it's really important that you have it done before the test. That'll tell you if you're ready or not. Okay? So again, that assignment is due for marks.